horas. Oh.
Alô, alô, let's fucking go. Chegamos, estamos de volta e hoje a gente tá na segunda parte de CS50. Isso é a primeira parte, basicamente, ainda, né? De CS50, eu tô fazendo aqui a primeira aula ainda. Que enrolação do cacete. Mas a semana aqui vai ser focada em terminar esta, esta paradinha, tá? A gente viu faz uma semana o CS50, né? Mas hoje a meta é pelo menos, cara, tentar terminar essa parada. Não terminar essa aula, mas chegar numa a parte do Scratch, baixar o Scratch, etc, né? E aí tá. Hoje a meta dessa semana é duas lives aqui de Odin, tá? Então é isso. Então hoje vai contar com uma live. Então eu vou focar porque ainda eu tô fazendo a bagulho da autoescola, então eu vou ter duas coisas de autoescola e dois de Odin. Perfeito, rapaziada. Então vamos embora. Odin. Então não vai ser 100% focado ainda no Odin, mas eu prefiro no Odin, no CS50, mas eu vou focar 100%, tá? Eu vou focar 100% aqui no que a gente pode. Eu sei que vai ser difícil não focar 100%. Tipo, nas próximas semanas eu vou tentar fazer 3 vezes. É fazer no final de semana, né? Contando no final de semana. Porque aí dia de semana, quando eu começar, eu não comecei ainda. Eu tô treinando aqui com meu pai, né? Já dirigi um pouco. Porém, eu ainda não comecei a fazer autoescola. Eu vou começar a fazer agora, né? Tô fazendo com o instrutor. Mas eu comecei a fazer autoescola mesmo. Porque eu acho que é autoescola melhor. E aí eu acho que vai ser as próximas semanas aí. Mas vambora. E por que eu não consigo carregar isso aqui, cara?
Solve problems. Well, the secret sauce in the middle.
Tá. Por que eu não escuto?
X is going to somehow involve permuting those zeros and ones into patterns, or equivalently, into the numbers that they represent. But if we now have a way to represent all inputs, in the world, be it letters, numbers, images, videos, anything else, and get out.
Tipo, o mais difícil vai ser semana que vem, que é semana. Puta. Né? Essas semanas, né? Que a gente vai fazer C, arrays, algorithms, memory, oh, memory,
Memory.
memory, um, data structures, structure, structure, structures, structures, structure, 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 Então, data structure, Python. Não. Então, esse aqui vai ser os mais difíceis, parece, aparentemente. Então, o C vai ser uma linguagem que a gente vai aprender. A gente já viu JavaScript, né?
Output from some problem-solving process, like how do we actually solve problems? Well, the secret sauce in the middle here is another term that you've probably heard in the real world nowadays, which is that of algorithm, step-by-step instructions for solving some problem. So this ultimately is what computer science really is about too, is not just representing information, but somehow processing it, doing something interesting with it to actually solve the problem that you've been provided as input so you can output the correct answer. Now, there's all sorts of algorithms implemented in our phones and in our Macs and PCs, and that's all software is. It's an implementation in code, be it C++ or Java or anything else, other languages exist too, in code that the computer understands, but it's still just step-by-step instructions. And among the things we'll learn in CS50 is how to express yourself in different ways to solve problems, not only in different languages, but using different methodologies as well. Because as we'll see, among the reasons we introduce these several languages is you don't just learn more and more languages that allow you to solve the same problems. Different languages will allow you to solve different problems and even save you time by being better tools for the job. So here, for instance, on an iPhone is maybe a bunch of contacts, which is presumably familiar, where we might have a whole bunch of friends and family and whatnot, alphabetized by first name or last name. And suppose we want to find one such person like John Harvard, whose number here might be +1 949 468 2750. Feel free to call or text him sometime. This is the goal of this problem. If we have our contacts app and I start typing in John's name by first name or last name, the autocomplete nowadays kicks in and it somehow filters the list down from my 10 friends or 100 friends or 1,000 friends into just the single directory entry that matches. So here too, back in the days of RG&B projector, we had phone books like this here too. I'm pleased to say, thanks to our friend Alexis, this is the largest phone book that we've used for this demonstration. This is an old school phone book that's essentially the same thing as our contacts app or address book nowadays, whereby I've got a whole bunch of names and numbers alphabetically sorted by first name or last name, whatever, and corresponding to each of those is a number. So back in the day, and frankly, even nowadays in your phones, how do you go about finding someone in a phone book or your contacts app? Well, you could very naively just start at the beginning and look down and just turn one page at a time, looking for John Harvard in this case. Now, so long as I'm paying attention, this step-by-step process will get me to John Harvard. Like, this is a correct algorithm, even though you might kind of object to how I'm doing this. Why? Like, what's bad about this algorithm? It's just slow. I mean, this is crazy slow. If there's like 1,000 pages in this phone book, which looks like there are, like this could take me as many as 1,000 pages, or maybe he's roughly in the middle, so like 500 pages. Like, that's crazy. That's really rather slow, especially if I'm going to do this again and again. Well, what if I do it a little smarter? Grade school, I sort of learned how to count 2 at a time. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, if I'm paying attention, I'll get there twice as fast because I'm counting 2 at a time. But is that algorithm step by step correct? And I'm seeing no, but why? I might skip over John Harvard. So just by bad luck and kind of with 50-50 probability, he's going to be sandwiched between 2 of the pages. Now, I don't have to abort this algorithm altogether. I could just, as soon as I get past the J section, if we're doing it by first name, I could just double back 1 page and just make sure that I haven't missed him. So it's recoverable, and this algorithm, therefore, is sort of twice as fast, plus 1 extra step maybe to double back. But that's arguably otherwise a bug or a mistake in the algorithm if I don't fix it intelligently. But what did we do back in the day? And what does your iPhone or Android phone do? What they typically do is they go roughly to the middle, look physically or virtually down. They see, oh, I'm in the M section. And so which side is John Harvard to the left or to the right? So he's to the left. So I could literally now, Jesus Christ. We talked about this before class, that this might be more, oh my God. There we go. We can tear the problem in half. Thank you. It's been a while. We can tear the problem in half. We know that John Harvard is to the left, so I can throw half of the problem away if dramatically, such that I'm now gone from a 1,000-page problem to 500 pages instead. What now can I do? I can go roughly to the middle here, and maybe I'm in the E section. So I went a little too far back to the left, but I kept it simple, and I just divided so that I can conquer this problem, if you will. And if I'm in the E section now, is John Harvard to the left or to the right? To the right, so I can again, Jesus Christ. Tear the problem in half. And now, thank you. So now John Harvard, again, is going to be in this half. I can throw this half away. So now I've gone from 1,000 to 500 to 250, and I can repeat down to 125, half of that, half of that, half of that, until I'm left with, finally, just a single page. And John Harvard is hopefully now on this page, such that I can call him, or not at all, at which point this is all sort of for naught. But what's powerful about each of those algorithms is that they're sort of good, better, and best. Like they all get the job done, conditional on the second one having that little fix, just to make sure I don't miss John Harvard between two pages. But they're fundamentally different in their efficiency and the quality of their design. And this is really representative of one of the emphases of a class like this. It's not just about writing correct code or getting the job done, but doing it well and doing it quickly, using the least amount of CPU or computing resources, using the minimal amount of RAM, using the fewest number of people, using the least amount of money. Whatever your constrained resource is, solving a problem better. So that first algorithm, step-by-step instructions, was all about doing something like this, whereby the first algorithm, if we plot things on a grid like this, we have on the x-axis a representation of the size of the problem. So this would mean small problem, like 0 pages. This would mean big problem, like 1,000 pages. And on the y or vertical axis, we have some measurement of time. So this is the number of seconds. Or the number of page turns, whatever your metric actually is. So this would be not much time at all, so fast. This would be a lot of time, so slow. So what's the relationship if we just roughly draw these three algorithms? Well, the first one is technically a straight line. And we'll describe that as n. The slope is n, because if you think of n as a number for the number of pages, well, there's a one-to-one relationship in the first algorithm as to how many times I have to turn the page based on how many pages there actually is. And you can think about this in the extreme. If I was looking for someone whose name started with Z, I might have to go through like 1,000 darn pages to get to that person whose name started with Z, unless, again, I do something hackish and just kind of cheat and go to the end. If we execute these algorithms again and again the same way, that's going to be pretty slow. But the second algorithm was pretty much twice as fast, plus that one extra step potentially, but it's still a straight line. Because if there's 1,000 pages, and I'm dividing the problem, I'm doing 2 pages at a time, well, that's like n divided by 2 steps, plus 1, give or take. But it's still a straight line but it's still better. Notice, if this is the size of the problem, 1,000 pages for instance, we'll notice that the first algorithm took literally twice as much time as the second algorithm. So we're doing better already. But the third algorithm, fundamentally, it's going to look something like this. And if you remember your logarithm, so to speak, sort of the opposite of an exponential, this curve is so much lower and flatter, if you will, than either of these two. Mathematically, more on this another time, the slope is going to be like log base 2 of n, or just logarithmic in nature. But what it means is that it's growing very, very, very slowly. It's still going up. It's never going to flatline.
Isso aqui é por causa do que ele vira exponencial do 2, né?
And go perfectly horizontal, but it goes up very slowly. Why? Well, if you think about two towns nearby, like Cambridge on this side of the river and the town of Alston on the other, suppose that they still have phone books like this one, and they merge their phone books for whatever reason. So overnight, we go from a 1,000-page phone book to a 2,000-page phone book. The first algorithms going to take literally twice as long, as will the second one, because we're only going through it 1 or 2 pages at a time. But if the phone book size doubles from this year, for instance, to next year, you can kind of in your mind's eye think about the green line. It's not going to go up that much higher. Why? Well, practically speaking, even if the phone book becomes 2,000 pages long, well, how many more times do you have to tear or divide that problem in half? Just one, because you're taking a 1,000-page bite out of it, or 500, then a 250. You're taking much bigger bites out of it than just one or two at a time. And so what computer science and what algorithms and about good design is about is figuring out what is the logic via which you can solve problems not only correctly, but efficiently as well. And that then gives us these things called algorithms. And when it comes time to code, which we're about to do too, code is just an implementation in a language the computer understands of an algorithm. Now, this assumes that we've come up with some digital way, that is to say 0 and 1 based way, to represent names and numbers. But honestly, we already did that. We came up with ASCII and then Unicode to represent the names. Representing numbers is even easier than that. That's really where we started. So code is just about taking as input some standardized representation of names and numbers and spitting out answers. And that's truly what iOS and Android are doing. When you start doing autocomplete, they could be searching from the top to the bottom, which is fine if you've only got a few friends and family in the phone. But if you've got 1,000, or if you've got 10,000, or if it's not a phone book anymore, it's some database with lots and lots of data, well, it stands to reason that it'd be nice maybe if the computer kept it all alphabetized, just like that book, and jumped to the middle, then the middle of the middle, then the middle of the middle of the middle, and so forth. Why? Because the speed is going to be much, much faster, logarithmic in nature, and not linear, so to speak, in nature. But we'll revisit those topics as well. But for now, before we get into actual code, let's talk for a moment about pseudocode. So pseudocode is not one formal thing. Every human will come up with their own way of representing pseudocode. It's an English-like or human-like formulation of step-by-step instructions, just using terse, correct English, or whatever human language. So for instance, if I want to translate what I did somewhat intuitively with that phone book by just dividing in half into step-by-step instructions I could hand you, or nowadays like a robot or something like that, well, step 1 was essentially to pick up the phone book, which I did. Step 2 was I opened to the middle of the phone book in the third and final algorithm. Step 3 was look at the page, as I did. Step 4 got a little more interesting. Even though I didn't verbalize this, presumably I was asking myself a question. If the person I'm looking for, John Harvard, is on the page, then I would have called him right then. But if he weren't on the page, if he instead were earlier in the book, as did happen, well, then I'm going to go to the left, so to speak. But more methodically, I'm going to open to the middle of the left half of the book. Then I'm going to go back to line 3. That's interesting. We'll come back to that in a moment. But else, if the person is later in the book, well, I'm going to open to the middle of the right half of the book and then go back to line 3. Now, let's pause here. Why do I keep going back to line 3? This would seem to get me doing the same thing forever, endlessly, but not quite. Why? Yeah, so because I am dividing the problem in half, for instance, on line 6 or line 9, implicitly, just based on how I've written this, the problem's getting smaller and smaller and smaller. So it's fine if I keep doing the same logic again and again, because if the problem's getting smaller, eventually it's going to bottom out, and I'm going to have just one person on that page that I want to call, and so the algorithm's done. But there is a perverse corner case, if you will, and this is where it's ever more important to be precise when writing code and anticipate what could go wrong. I should probably ask one more question in this code, not just these 3. What might that question be? Yeah. Yeah, so if John Harvard is not in the book, there's this corner case where what if I'm just wasting my time entirely and I get to the end of the phone book and John Harvard's not there? What should the computer do? Well, as an aside, if you've ever been using your Mac or PC or phone and the thing just freezes, or like the stupid little beach ball starts spinning or something like that, and you're like, what is going on? Some human at Google or Microsoft or Apple or the like made a mistake. They forgot, for instance, that 4th uncommon but possible situation wherein if they don't tell the computer how to handle it, the computer is effectively going to freak out and do something undefined, like just hang or reboot or do something else. So we do want to add this, else quit altogether. So you have well-defined behavior. And truly think that the next time your computer or phone spontaneously reboots or dies or does something wrong, it's probably not your fault per se. It's some other human elsewhere did not write correct code. They didn't anticipate cases like these. Well, now let's use some terminology here. There's some salient ideas that we're going to see in Scratch and C and Python and these other languages I alluded to earlier. Everything I've just highlighted here, henceforth, we're going to think of as functions. Functions are verbs or actions that really get some small piece of work done for you. Functions are verbs or actions. Here, though, highlighted is the beginning of what we'll call conditionals. Conditional is like a fork in the road. Do I go this way? Do I go this way? Or some other way altogether? How do you decide what road to go down? We're going to call these questions you ask yourself Boolean expressions, named after a mathematician, Boole. And a Boolean expression is just a question that has a yes or no answer, or a true or false answer, or a 1 or 0 answer. Just it's a binary state, yes or no, typically. Otherwise, we have this, go back to, which is what we're generally going to call a loop, which somehow induces cyclical behavior again and again. And those functions and those conditionals, Boolean expressions and loops and a few other concepts are pretty much what will underlie all of the code that we write, whether it is in Scratch, C, or something else altogether. But we need to get to that point. And in fact, let's go and infer what this program here does. At the end of the day, computers only understand zeros and ones. So I claim here is a program of zeros and ones. What does it do? Anyone want to guess? I mean, we could spend all day converting all of these zeros and ones to numbers, but they're not going to be numbers if it's code. What do you think? That's amazing. It does, in fact, print hello world. All right, so no one, except like maybe you and me and a few others in the room, should know, and that was probably guess, admittedly, or advancing on the slide. But why is that? Well, it turns out that not only do computers standardize information, data, like numbers and letters and colors and other things, they also standardize instructions. And so if you've heard of companies like Intel or AMD or NVIDIA or others, among the things they do is they decide as a company what pattern of zeros and ones shall represent what functionality. And it's very low-level functionality. Those companies and others decide that some pattern of zeros and ones means add two numbers together, or subtract, or multiply. Another pattern might mean load information from the computer's hard drive into memory. Another might mean store it somewhere else. Another might mean print something out to the screen. So nested somewhere in here, and admittedly I have no idea which pattern offhand because it's not interesting enough to go figure it out at this level, says print. And somewhere in there, like this gentleman proposed, I bet we could find the representation of H, which was 72, and E, and L, and L, and O, and everything that composes hello world. Because as it turns out, in programming circles, the very first program that students typically write is that of hello world. Now, this one here is written in a much more intelligible way. Even if you're not a programmer, odds are if I asked you, what does this program do, you would have said, oh, hello world, even though there's a lot of clutter here. Like, no idea what this is until next week. Int main void, that looks cryptic. There's these weird curly braces, which we rarely use in the real world. But at least I understand a few words like hello and world. And this is kind of familiar, printf, but it's not print, but it's probably the same thing. So
Então, isso aqui a gente vai aprender semana que vem. Nessa semana eu quero terminar o bagulho do Scratch. Quero fazer o projeto. Então, final de semana eu vou focar. E quinta, focar também pra fazer o projeto do Scratch. E, mano, se eu peguei na faculdade, e é difícil pra caralho, mas se tem a lógica, tu consegue pegar. Se tem a lógica, né? Obviamente que a gente vai ver memória, a gente vai ver estrutura de dados, etc, que vai ser mais foda. Mas eu vou ver na faculdade de novo. Mas acho que vai ser interessante. É mais que, mano, é massa, tá ligado? E isso é legal. A gente vai aprender. Antes eu usava tipo um bagulho lá da minha faculdade retrasada que eu fiz. Mas eu fiz mais com o uso de IA. Então,
So here too is an example of this hierarchy. Back in the day, in the earliest days of computers, humans were writing code by representing zeros and ones. If you've ever heard your parents talk about punch cards or the like, you're effectively representing patterns that tell the computer what to do or what to represent, like literally holes in paper. Well, pretty quickly early on, this got really tedious, only writing code at such a low level. So someone decided, you know what? I'm going to put in the effort. I'm going to figure out what patterns of zeros and ones I can put together so as to be able to convert something more user-friendly to those zeros and ones. And as a teaser for next week, that person invented the first compiler. A compiler is just a program that translates one language to another. And more modernly, this is a language called C, which we'll spend a few weeks on together because it's so fundamental to how the computer works.
Wordinho aqui, né?
Hey folks, I just want to explain how to properly learn programming. The most common mistake I see is that people just read the text and copy the code, and that's it. If you just find item in list, one has to put the 0 right here. So let me move this down a little bit.
works, even this is going to get tedious by like week 6 of the class, and this is going to get stupid, this is going to get annoying, this is going to get cryptic. We're just going to write print hello on the screen in order to use a different language called Python. Why? Because someone wrote in C a program that can convert Python, this is a white lie, to C, which can then be converted to zeros and ones, and so forth. So in computing, there's this principle of abstraction, where we start with the basics, and thank God we can all trust that someone else solved these really hard problems way long ago. Then they wrote programs to make it easier. We write programs to make it easier. You can now write code like I did with the chatbot to make things even easier. Why? Because OpenAI and other companies have abstracted away a lot of the lower level implementation details. And that's where I think this stuff gets really exciting. We can stand on the shoulders of others so long as we know how to use and assemble these kinds of building blocks. And speaking of building blocks, let's start here. Now, odds are some of some of you might have started here in like grade school playing with Scratch, and it's great for like after school programs, learning how to program. And you probably used this language to make games and graphics and just maybe playful art or the like. But in Scratch, which is a graphical programming language designed about 20 years ago from our friends down the road at MIT's Media Lab, it represents pretty much everything we're going to be doing fundamentally over the next several weeks in more modern languages like C and Python, more textual languages, if you will. I bet I could ask the group here, what does this program do when you click a green flag? Well, it says hello world on the screen. Because with Scratch, you have the ability to express yourself with functions and loops and conditionals and all of this, but by using drag and drop puzzle pieces. So what we're about to do is this. We're going to go on my screen to scratch.mit.edu. It's a browser-based programming environment. And we're only going to spend 1 week, or really a few days, in CS50 on this language. But the overarching goal is to, one, make sure everyone's comfortable applying some of these building blocks and actually developing something that's interesting and visual and audio as well. But to also give us some visuals that we can rely on and fall back on when all of those curly braces and parentheses and sort of stupid syntax comes back that's necessary in many languages, but can very quickly become a distraction early on from the interesting and useful ideas. So what we're about to see is this in a browser. This is the Scratch programming environment, and there's a few different parts of this world. This is the blocks palette, so to speak. That is to say, there's a bunch of puzzle pieces or building blocks that represent functions and conditionals and loops and other such constructs. There's going to be the programming area here where you can actually write your code by dragging and dropping these puzzle pieces. There's a whole world of sprites here. By default, Scratch is a cat by design, but you can make Scratch look like a dog, a bird, a garbage can, or anything else, as we'll soon see. And then this is the world in which Scratch itself lives. So Scratch can go up, down, left, right, and generally be animated within that world. For the curious, kind of like high school geometry class, there's sort of this xy plane here. So 0, 0 would be in the middle. 0, 180 is here. 0, comma, negative 180 is here. Negative 240, 0 is here. And positive 240, 0 is here. Generally, you don't need to worry about the numbers, but they exist so that when you say up or down, you can actually tell the program, go up 1 pixel, or 10 pixels, or 100 pixels, so that you have some definition of what this world actually is. All right, so let's actually put this to the test. Let me go ahead here and flip over to, in just a moment, the actual Scratch website, whereby I'm going to have on my screen in just a moment that same user interface, once I've logged in, that via which I can actually write some code of my own. Let me go ahead and zoom in on the screen a little bit here. And let's make the simplest of these programs first. Maybe a program that simply says hello world. Now, at a glance, it's kind of overwhelming how many puzzle pieces there are. And honestly, even over 20 years, I've never used them all. And MIT occasionally adds to it. But the point is that they're color-coded to resemble the type of functionality that they offer. And also, it's meant to be the sort of thing where you can just kind of scroll through and get a visual sense of like what you could do, and then figure out how you might assemble these puzzle pieces together. So I'm going to go under this yellow or orangish category here to begin with. So there exists in the world of Scratch not quite the same jargon that I'm using now, functions and conditionals and loops. That's more of the programmer's way. This is more of the child-friendly way, but it's really the same idea. Under events, you have puzzle pieces that represent things that can happen while the world is running. So for instance, the first one here is sort of the canonical when the green flag is clicked. Why is that relevant? Well, in the two-dimensional world that Scratch lives in, there's a stop sign, which means stop, and there's a green flag, which means go. So I can therefore drag one of these puzzle pieces over here so that when I click that green flag, the cat will in fact do something for me. It doesn't really matter where I drop it, so long as it's somewhere in the middle here. I'm going to go ahead and let go. Now, I want the look of the cat to change. I want to see like a cartoon speech bubble come out for now. So I'm going to go under looks here. And there's a bunch of different ways to say things and think things. I'm going to keep it simple and just drag this one here. And now notice when I get close enough to that first puzzle piece, they're sort of magnetic and they want to snap together. So I can just let go and boom, because they're a similar shape, they will lock together automatically. And notice too, if I zoom in here, the white oval, which by default says hello, is actually editable by me. Because it turns out that some functions can take arguments, or more generally, inputs that influence their behavior. So if I kind of click or double click on this, I can change it to the more canonical, hello world, or hello David, or hello whatever I want the message to be. I'm going to go ahead and zoom out. And now over here at top right, notice that I can very simply click the green flag, and I'll have written my first program in Scratch. I clicked the green flag. It said go. And now notice it's sort of stuck on that because I never said stop saying go. But that's where I can click the red stop sign and sort of get the cat back to where I want it. So think about for just a moment what it is we just did. So at the one hand, we have a very obvious puzzle piece that says say, and it said something, but it really is a function. And that function does take an input, represented by the white oval here, otherwise known as an argument or a parameter. But what this really is just an input to the function. And so we can map even this simple Scratch program onto our model of problem solving before, with an addition of what we'll call, moving forward, a side effect. A side effect in a computer program is often something
Oh, I love trash. Anything dirty or dingy or
that happens visually on the screen, or maybe audibly out of a speaker. It's something that just kind of happens as a result of you using a function, like a speech bubble appearing on the screen. So here, more generally, is what we claimed it represents the solving of a problem. And let's just consider what the input is. The input to this problem, say something on the screen, is this white oval here that I typed in, hello world. The algorithm, the step-by-step instructions, are not something really I wrote. Like our friends at MIT implemented that purple say block, so someone there knows how to get the cat to say something out of its comical mouth. So the algorithm implemented in code is really equivalent to the say function. So a function is just a piece of functionality implemented in code, which in turn implements an algorithm. So algorithm is sort of the concept, and the function is actually the incarnation of it in code. What's the output? Well, hopefully, it's this side effect, seeing the speech bubble come out of the cat's mouth like this. All right, so that's one such program, but it's always going to play and look the same. What if I actually want to prompt the human for their actual name? Well, let me go back to the puzzle pieces here. Let me go ahead and throw this whole thing away. And if you want to delete blocks, you can either right click or control click and choose from a menu, or you can just drag them there and sort of let go, and they'll disappear. I'm going to go back in and get another event block, even though I could have reused that same one. I'm going to go ahead and go under sensing now. And if I zoom in over here, you'll see a whole bunch of things, like I can sense distance and colors. But more pragmatically, I can use this function in blue, ask something, and then wait for the answer. And what's different about this puzzle piece is that it too is, yes, a function. It too takes an argument. But instead of having an immediate side effect like displaying something on the screen, it's essentially inside of the computer going to hand me back the response. It's going to return a value, so to speak. And a return value is something that the code can see, but the human can't. A side effect is something the human sees, but a return value is something only the computer sees. It's like the computer is handing me back the user's input. So how does this work? Well, notice, and this is a bit strange, this isn't usually how variables work, but Scratch 2 supports variables. And that was a word I used quickly at the very start when we were making the chatbot. A variable, like in math, X, Y, or Z, just stores some value. But it doesn't have to store a number. In code, it can store like a human name. So what's going to happen when I use this puzzle piece is that once the human types in their name and hits enter, MIT, or really Scratch, is going to store the answer, the so-called return value, in a variable that's designed to be called answer. But as we'll see, you can make your own variables down the line if you want and call them anything you want. But let me go ahead and zoom out. Let me drag this over here. I'm going to use the default question, what's your name? But I could certainly change the text there. And let me go under looks again. Let me go ahead and grab the say block.
Vai fazer o quê?
And let me go ahead and say, just for consistency, like hello, comma, okay. And now let me go under maybe sensing. I want to say, I want to say this answer. Well, notice this. The shapes are important. This too is an oval, even though it's not white, but that's just because it's not editable. It's going to be handed to me by the ask function. Let me zoom out and grab a second say block like this. And notice it will magnetically clip together. I don't want to say hello again, so I could delete that. But now it's still the same shape, even though it's a little smaller. Let me go back to sensing and notice what can happen here. When you have values, like words, inside of a so-called variable, you can use those instead of manual input at your keyboard. And notice it too wants to magnetically slap into place. It'll grow to fit that variable because the shape is the same. And now let's do this. Let me click the green flag at right. I'm seeing, quote unquote, what's your name? I'm getting a text box this time, like on a web page, for instance. Let me type in my name and watch closely what comes out of the cat's mouth as soon as I click the check mark or hit enter. Huh. OK, got my name right, but let me do it once more. Let me stop and start. DAVID. Enter. No, it didn't work. Let me try one other. Maybe it's my name. Let's try Kelly. Enter. What's missing, obviously? The hello, there's a bug, a mistake in this program. But is there? Like, what explains this? Even if you've never programmed before, intuitively, what could explain why I'm not seeing hello? Exactly. It's on two different lines, so it's doing one after the other. So it is happening. It's just you and I, as the slowest things in the room, are just not seeing it in time because it's happening so darn fast. Because my computer is so new and so fast, it's happening but way too quickly. So how can we solve this? Well, we can solve this in a few different ways. And this is where, in Scratch, at least for problem problems at 0 wherein you'll have an opportunity to play around with this, I can scroll around here and, OK, under control, I see something like wait. So I can just kind of slow things down. And now notice, too, if you hover over the middle of two blocks, if it's the right shape, it'll just snap into the middle, too. Or you can, just so you know, kind of drag things away to magnetically separate them. But this might solve this. So let me hit stop and then start. DAVI. ID, enter. Hello, David. All right, that was a little, let's do like maybe 2 seconds to see it again. Green flag, DAVID, enter. Hello, David. All right, it's working better. It's sort of more correct because I'm seeing the hello and the David, but kind of stupid, right, to see one and then the other. Wouldn't it be nice to say it all in one breath, so to speak? Well, here's where we can maybe compose some ideas. So let me get rid of this wait and the additional block. Let's confine ourselves to just one say block. But let me go down to operations, where we haven't been before. And this is interesting. There's this bigger oval here that says join two things, like apple and banana. And those are just random placeholder words that you can override with anything you want. But they're both ovals and white, which means I can edit them. So let me go ahead and do this. Let me drag this on top of the say block. And this is just going to therefore override the hello I put there. Now, I don't want to say apple or banana, but I do want to say hello, comma. And I then want to say my name. OK, so now I can go back to sensing, go back to answer, drag and drop this here. That'll snap into place. And let me zoom in. Now what I've done is take a function, and on top of it, I nested another function, the join function, that takes two arguments or inputs and presumably joins them together as per its name. So let's see what this does for us. Let me click stop and start. I'll type in David, enter. And it's so close. Now, this is just kind of an aesthetic bug. What have I done wrong here? There's no space, so it looks a little wrong. But that's an easy fix. I just need to literally go into the hello block after the comma, hit the space bar, so that now when I stop and...
Então, rapaziada, aqui, ó, quando eu chegar... Aqui agora já tá quase 9h40. E eu não quero foder meu sono. Quando a gente chegar mais ou menos... aqui, 1h30, encerra. E aí, quarta a gente termina e aí a gente já começa o Scratch pra domingo, não sábado, domingo a gente terminar. Tá.
Start again and type in David. Now I see something that's closer to the grammar.
Pra não foder o sono e também porque eu não vou conseguir prestar atenção, já tô ficando nos 11, tá ligado? Hoje eu meti um cardiozão maluco. Mas assim, eu tô anotando tudo, tá? Eu prefiro anotar no papel, mas eu não tô anotando no papel. Eu tô com o Scratch aberto. Mas eu tô anotando no Obsidian, tá?
Might typically expect syntactically here. All right, so let's model this after what we just saw earlier. We've now introduced a so-called return value. And this return value is something we can then use in the way we want. It's not happening immediately like the speech bubble. It's clearly being passed to me in some way that I can use to plug in somewhere else, like into that join block. So if we consider the role of these variables playing, let's consider the picture now as follows. If the input now to the first function, the ask block, is what's your name, quote unquote, that's indeed being fed into the ask block. And the result this time is not a speech bubble. It's not some immediate visual side effect. It is the answer itself, stored in a so-called variable, as represented by this blue oval. Meanwhile, what I want to do is combine that answer with some text I came up with in advance by kind of stacking these things together. Now, visually in Scratch, you're stacking them on top, but it's really that you're passing one into the other into the other. Because much like math, when you have the parentheses and you're supposed to do what's inside the parentheses and then work your way out, same idea here. You want to join hello and answer together, and whatever that output is, that then becomes the input to the say block, which, like in math, is outside of the join block itself. So pictorially, it might now look like this. There's two inputs to this story, hello, comma, space, and the answer variable. The puzzle piece in question is join. Its goal in life had better be to give me the full phrase that I want, hello, comma, David. Let's shift everything over now, because that output is about to become the input to the say block, which itself will now have the so-called side effect. And so this, too, is what programming, and in turn what computer science is about, is composing with the solutions to smaller problems, solutions to bigger problems, using those component pieces. And that's what each of these puzzle pieces represents, is a smaller problem that someone else, or maybe even you, has already solved. Now we can kind of kind of spice things up here. If I go back to Scratch's interface, we don't have to use just the puzzle piece here. I can do something like this. Let me go ahead and drag these apart and get rid of the say block. Down here, just for fun, there's all these extensions that you can add over the internet to your own Scratch environment. And if I go to like text-to-speech down here, I can, for instance, do a speak block instead of a say block, colored here in green. I can now reconnect the join block in here. And if we could raise the volume just a little bit, let me stop the old version, start the new version, type in my name, and hear what Scratch actually sounds like.
Hello, David.
OK, not very cat-like, but we can kind of waste some time on this by like dragging the set voice to box. And I can put this anywhere I want above the speak block. So I'm just going to put it here, even though I've already asked a question. Maybe kitten sounds appropriate. Let's try again. DAVID.
Meow, meow.
OK. And then let's say giant. A little creepier. Here we go. DAVID. And lastly?
Hello, David.
All right. A little ransom-like instead. All right. So that's just some additional puzzle pieces, but really just the same idea. But I like that we've introduced some sound. So let's
Então é isso, rapaziada. A gente parou aqui. Pelo jeito que a gente consegue colocar coisa. Então a gente parou aqui. A gente volta para essa lição quarta-feira. Hoje é porque eu tô bem cansado, mas eu consegui fazer bastante coisa, tá? E quinta-feira aí a gente volta, foi uma horinha. Mas quinta a gente termina e a gente já começa a fazer o project ali. A gente determina o que a gente vai fazer. E etc. O problem, né? Pelo que eu vi, dá pra gente vir aqui, né? Tutorial. Não, é no...
let's do this. We don't have to use just the puzzle piece here. I can do something like this. Let me go ahead and drag. Not very cat-like, but we can kind of waste some time on this by like dragging the set voice to box. Giant. A little creepier. Here we go. DAVID. And lastly?
Hello, David.
É isso.